This is an introduction to calculus by me, Terry Endicott. And first year calculus is broken down into two parts traditionally: differential calculus and integral calculus. And I'm not going to talk about integral calculus at this time. We'll talk about it a little bit later. But differential calculus. Now, differential calculus is the study of the derivative. Well, that's nice if you know what a derivative is, but you might not know. So I'm going to tell you. And to do so, I want to introduce you to a nice function. See, we know it's a nice function because it says so. Anyway, what the derivative basically is how rather than basically, I'll tell you what it is. At any given point, it'll be the slope of the tangent line. Now, we don't have the tangent line defined, but we know what the slope of a line is from college algebra and trig. By the way, let me make a side note. How much college algebra and trig do you know to do well in calculus? The answer is simple. That's not, there are maybe a couple of sections of college algebra and trig you might not need to know to do well in calc, but the more you know, the better. So might as well assume all. Most students who do not do well in calc actually don't do well because of poor college algebra and trig and not the calculus itself. Please don't be one of them. If your background is weak, strengthen it before you take calculus. It'll do both you and your instructor a favor. Anyway, mainly yourself, to tell the truth. Okay, let's get back to what differential calculus is about. It's the study of the derivative, which is the slope of the tangent line. Well, first of all, why would you want to study that? Well, let's take our nice little simple example here. There are a couple of places that are of really nice importance to us. For example, the thing seems to sort of hit a maximum there, the highest value the function can reach. However, we know that's not true. This actually happens to be a cubic, and if I were to extend this, this way, this is why I didn't draw it freehand, and it goes way off like that. Also, by the same token, it appears to have a sort of a minimum here, but you can obviously see from this graph that that's not really a minimum because this guy here is lower than that. These are what's known as local extrema. And what is characteristic about that is that right at the top before it goes down, if I were to draw a tangent line, it'd be a horizontal line, i.e. slope 0. So if you knew the slope of the tangent line, i.e. the derivative at that point, and you could set it equal to 0, that would tell you something about this function. Now, admittedly, there are functions like y equals x cubed, for example, which is a nice little function, that have places where the derivative actually is 0, namely at 0, and the function doesn't peak out there or bottom out there, a local maximum nor a local minimum. But it does say something really interesting about that function, which we'll get into later at a different lecture. Now, another nice thing to look at is notice that this thing sort of goes like that, and this thing goes like that. In other words, this cups down, this sort of cups up. Concave down, concave up. Well, there's a point here, boink, about there, called a point of inflection. And a point of inflection is, you get that by looking at the derivative also. Okay, so I've sort of beaten it to death that you want to look at the derivative because it tells you a lot about the function itself. Not just x cubed here. This is not x cubed, of course, but this is a cubic. Not just the function, this particular function, but other functions in general. And what other things does it tell you? Well, derivatives are used in a variety of things. And matter of fact, there's a whole topic called differential equations, which you just study equations involving derivatives and things that are used in real-life, worldly applications. Use something even more complex than that called partial derivatives. And you study in engineers, physicists, etc., and maybe even a few mathematicians study partial differential equations. Tell the truth, my background's in theoretical mathematics, and I stay away from partial differential equations. But anyway, that's just me. Okay, so let's just put our nice function to the side here, up on the floor. And let's see, let's draw a nice little another function. Okay, no idea what that is. It looks like a squiggly. And let's say you want to find the derivative near, oh, let's pick a point. How about this point here? Okay? How would one go about doing that? One could just lay down a straight edge and go like that and guess at it. And admittedly, in some applications, that might be the fastest way of doing it. But in general, it's not a good idea. I mean, it's just not that productive. One thing you can do is we want to get the slope of the tangent line. With in mind that we have never defined what the tangent line is. Actually, what we're going to do is end up sort of, saying, well, what it should do is look like this, and we'll get what's known as a derivative, and then define the tangent line after the derivative to tell the truth. Sort of seems backwards, but this is just, well, I guess you call it heuristics. We want to, we have something we want to go for and see how we want to do it. We're going to do it. Okay, so now, let's take a point. Let's get rid of this as function so I can write. Okay, bye-bye. And let's call this point a comma f of a. It was very original. My function is called f. Could have called it g, or sigma, or Alfred. Okay. Let T be a point close to A. Okay, so let's say the axis is down here someplace. Here's A, and let T be, let's say, here. And then what we want to do is look at the slope on the line that goes a comma f of a and t comma f of t. So that's point there is t comma f of t, right? So what I want to do, I'm carrying this just for looks, is let's draw a line there. Might as well just carry it for looks, draw a lousy line there. Okay, it's the bottom line there, not the top one. I should have just erased both, but I didn't want to erase my curve. Okay, so this guy, we want the slope of that one. So what we do to get the slope is it's just over rise divided by run. So it's f of t minus f of a divided by t minus a, when t is close to a. And what we're going to do is the next time we'll talk about limits and actually define the limit of this as t approaches a and call that the derivative. So this is cute with little squiggly functions, you know. But let's say we have a real life example. And here's my real life example. This is real life example. I know my jokes aren't funny, that's why I have this day job. Anyway, at 2, okay, the function of is y equals x squared, right? I hope so. Notice the scale is a lot different. You know, what is about 1 unit here is actually a little bit over 5 units there. So, and I knew what the derivative was, so I just actually drew this out. And by the way, this was done with Excel. And one of these days I'll show you how to do things with Excel and stuff where you can draw real quick drafts real fast. Okay. We have this point here, and this is at 2, 4, and we want to know what the derivative is at that point. And the derivative is not that line, it is the slope of that line. And if this were at a 1-to-1 scale, you would see that that line's fairly fairly steep, not fast. Lines are neither fast nor slow. It's fairly steep, and actually the derivative is 4. So let's see what we can do. And what I did here, with the magic of Excel, is I drew another. Same graph actually. Scale's a lot different, but it's a little bit, it's just a section of where I was at. This is wrong. This is supposed to be 2 here. My scale got all screwed up. And this is 0 actually. And this is 1, and this is 3. I can see the scale got goofed up. Anyway, and then this scale is goofed up too, because this is at 4. This is 2, 4. But you can see here what we want to do. What I'm going to do is pick a t. So this is t, t squared. And I'm going to do a tangent line through that point, and this one, I'll try not to screw this baby up. Okay, get the slope of that line, and then what we'll pretend to do is let t vanish. So let's just sort of push this aside and look at it. What we want is slope, we'll call it s. This is actually going to be a function of t, by the way. S of t. Okay, it's going to be the function evaluated at t minus the function evaluated at some fixed point, and I called it a before. Let's be consistent right now. There's nothing sacred about a. It was a few minutes ago. Let's keep it a. Tomorrow it could be b, z, or whatever. Divided by t minus a. Okay? Now, in this case, f of any value here, call it x, this, I don't want to confuse with that t, is x squared. So what would this be? This will be x squared. Oops, not x squared, it's t there. Rookie mistake. T squared minus, what's f of a? A is 2. So a squared will be 4 divided by t minus 2. Note, it's very important, t is not equal to 2. It's hard to draw a line between a point and itself, right? So what we want to do is we factor this, factor the numerator. It's t minus 2, t plus 2, difference of 2 squares here, t minus 2. This equals, now that's t minus 2 divided by t minus 2, which is 1, times t plus 2 is t plus 2. And that's true no matter where t is on here, as long as it's not equal to 2. I mean, here being the parabola y equals x squared. However, we want W-A-T-N is want. Cool, man. We want t close to 2. So, t plus 2 is close to, drum roll, 4. Okay? So, the derivative, and this is actually end up being the derivative when we take the limit, the derivative of x squared when x is equal to 2 is 4. So we've done our first derivative. Isn't that neat? Now the next time what I want to do is talk about limits and put some actual some definitions here and put things together, and we'll go on from there and learn how to differentiate things. Differentiating polynomials like x squared is really simple. Go through that and have a lot of fun. And we will stop right now. Enjoy.